74,000 years ago, on what would later be called the island of Sumatra, on a morning that behaved like any other morning, the northern summer monsoon was blowing out of the south. The sky was the pale blue of the tropics before the heat rises. The sea around the island was the color the sea is at that latitude, which is a color without a proper name in any human language. And 2.5 degrees north of the equator, in the place where the ocean floor slides under the continent at a few centimeters a year, 5 bodies of molten rock had been quietly finding each other inside the crust. They had been finding each other for a long time, centuries, maybe 1,000 years, no one was counting. Beneath a forested plateau 3 kilometers thick, beneath cool springs and sleeping animals and the soft breath of the morning, 5 separate chambers of magma had risen and merged and risen again, and the pressure inside them had become something that the rock above could no longer hold. You could not have heard anything from the surface. The mountain that sat above the plateau looked like other mountains. It had its own weather. It had clouds wrapped around its shoulders in the afternoon and then lost them again at dusk. It had forest on its flanks that had been there in different versions of itself for hundreds of thousands of years. It had the ordinary life of a tropical volcano, which is to say that on most days it did nothing at all. This is the morning that pattern ended. There was no warning in any language you would recognize. There was a tremor. There was a ground-shaking groan. There was, perhaps, a moment when the birds on the plateau lifted into the air the way birds do when they sense something the human body does not yet know how to feel. And then, for somewhere between 9 and 14 days, the top of the world poured itself into the sky. This is a story about that eruption. It is the story of the largest explosive volcanic event of the last 2.5 million years. It is the story of a column of superheated rock and gas that climbed 32 kilometers into the stratosphere, almost 4 times the cruising altitude of a modern airliner. It is the story of 3,800 cubic kilometers of Earth rearranged in less than a fortnight, and of an ash blanket that would eventually cover 7.5% of the planet's surface in a measurable layer of powdered rock. But it is also a story about silence, because by the time the eruption ended, the mountain that had done it no longer existed. It had emptied itself into the sky and collapsed downward into its own void, leaving a hole in the earth 100 kilometers long and 30 kilometers wide. The hole filled with water. The water became a lake, and in the center of the lake, over the centuries that followed, the floor of the crater slowly pushed back up and made an island. The island is still there. The lake is still there. The island is the size of Singapore. The lake is the size of a small country. And for most of human history, almost no one has known what it was. People fished in that lake for thousands of years before anyone understood it as the scar of an eruption. They built houses along its shore. They made boats. They watched the mist rise off the water in the mornings and the fish break the surface at dusk. And they did not know, and they had no way of knowing, that the water they lived beside was the place where, one morning, the sky turned. We know now. That is, to a first approximation, the difference between us and them. We have rocks in ice cores from the South Pole that record the moment the eruption happened. We have glass shards scraped from the lake bed of Lake Malawi, 9,000 kilometers to the west. We have radiometric dates from argon-argon thermochronology that bracket the event, the two most recent of which, done with high-precision laboratory techniques, put it at 73,880 years ago, plus or minus 320, and 73,700, plus or minus 300. These numbers are as close as human instruments can come to pointing at a specific morning more than 700 centuries in the past. We also know the shape of the eruption. We know it was not one explosion. It was a sustained release of material from the magma chamber below, beginning with a limited fall of tephra that might have felt at the edges like a heavy rainstorm of grit, and then moving into the main phase, which was ignimbrite. Ignimbrite is the word volcanologists use for the slow, dense, gravity-driven flow of superheated rock that rolls outward from a collapsing eruption column. It does not roar across the landscape like a river. It pours. It spreads out at hundreds of kilometers per hour on the flat, and it fills every valley on its way, and it arrives at the sea, and then it continues into the sea. Inside the Toba caldera, in places, the ignimbrite deposit is over 600 meters thick. 600 meters. Think of a building 200 stories tall, and then think of the rock that used to be above your head, now laid flat in a ring around the place you were standing. This is the geography of what happened. 74,000 years ago, in what is now Indonesia, a volcano called Toba erupted. The eruption had a volcanic explosivity index of 8, which is the highest category the scale has. There have been fewer than a dozen eruptions of this class in the known geological record, and Toba was one of them. It is called now the Youngest Toba Tuff. The name makes it sound gentle. It is not gentle. It is the last of 4 caldera-forming eruptions at the same place over 1.2 million years. Each of those eruptions was enormous. Each collapsed a mountain. Each opened and closed and reopened a wound in the skin of the planet. We do not have good witnesses for the earlier 3. We have only the Toba we know tonight, the most recent, the best studied, the one whose ash we can still find in lake beds and hillsides and the drill cores of ships in the middle of oceans. And this most recent one, the one we will be thinking about tonight, had a consequence we are still not finished debating. Something happened to us, to the species that would eventually look up from a cave floor in Africa and invent the word for ash. Something happened to our numbers around the same time. Our mitochondrial DNA narrows in the deep record to a thin thread. Our whole genome simulations find a bottleneck. Our effective population falls to perhaps a few thousand breeding pairs. And for almost a century, one particular generation of paleoanthropologists has pointed at this eruption and said, "This is why. This is the winter that almost ended us." And then, over the last 20 years, Another generation of scientists has gone to Lake Malawi and to the Jureru Valley in southern India and to polar ice cores, and has come back with a quieter answer. Perhaps, perhaps not. Perhaps the winter was shorter than we thought. Perhaps the crash was a story we told to explain a silence that the genomes had already created by themselves. Perhaps the ash fell and the earth cooled, and the people and animals of 74,000 years ago looked up and thought, "This is a very strange year." And then the year passed and the world kept turning. Or perhaps not. The honest answer is that even now, after decades of work by hundreds of scientists across continents, we do not fully know. The ash is real. The sulfate in the ice cores is real. The bottleneck in our genome is real. But the line between them, the causal line that connects one morning in Sumatra to the near extinction of a species in Africa and the Near East, is the kind of line that physics and biology have struggled to draw. Some of the sharpest arguments in quaternary science are about exactly this. This is a story about uncertainty. It is a story about what we can and cannot know about a morning that happened before there were calendars. It is a story about the specific material of the Earth, about sulfur and silicate and tephra, about three distinct physical records that we have learned to read. The ash itself, stratified now in riverbanks and lake beds from South Africa to the South China Sea. The sulfate spike that lies in an ice layer at the South Pole and another one in Greenland, precisely aligned to each other, and the coiled genetic memory in your own body. The part of you that was assembled from a small handful of ancestors during a window of time that you carry with you and have no memory of. These three records do not all agree. The ash says the eruption was vast. The sulfate says the cooling was real. The genomes say something complicated, something that depends on how you do the math, on which populations you sample, on how you define the word bottleneck. And the archaeology, when we dig, sometimes says the people on the ground barely noticed. Tonight, we will let them argue. We will spend 2.5 hours in the company of what one morning, 74,000 years ago, did to the atmosphere and to the rock and to the water and to the people who did not know a thing was happening. We will stand above the caldera before it was a caldera. We will watch the eruption without being destroyed by it, because we are protected by time. We will follow the ash west across the Indian Ocean and south to Africa and north to the polar ice. We will look at what the scientists thought in the 1990s and what they think now, and we will let both speak. We will meet a few dozen researchers by name, people who spent their careers in labs and lake cores and rock outcrops, trying to decide what this morning meant. And then we will return to the lake itself. A lake in Sumatra, 100 kilometers long, 30 kilometers wide. A calm sheet of water in the tropics, with fishing villages along its shore, with an island in its middle that holds a culture older than many of the world's nations. A geopark now, a tourist destination, a quiet place. A quiet place that once, for 2 weeks, was the loudest place on Earth. It is worth pausing for a moment on the word supereruption. The word did not exist when geologists first began to study the layer of ash around the Indian Ocean that we now attribute to Toba. For most of the 20th century, the word used was simply eruption, and the comparisons made were to events like Krakatoa in 1883 or Tambora in 1815, or the Mount St. Helens event of 1980. Those were the largest events in the living memory of volcanology. But Toba is not in the living memory of anyone. The word supereruption was coined in part because existing vocabulary was failing. A supereruption is defined as a volcanic event with a volcanic explosivity index of 8 or above, meaning an erupted volume of at least 1,000 cubic kilometers. Toba, at an estimated 3,800 cubic kilometers of dense rock equivalent, exceeds that threshold by almost 4 times. It is, in the ordinary sense of the word, off the scale. There is no volcano alive today that has demonstrated the capacity to do what Toba did. There are candidates. There are calderas at places like Yellowstone in the American West, and at Campi Flegrei outside Naples, and at Taupo in New Zealand, and at Aira in Japan that have, in their own pasts, produced eruptions of similar class. We watch those calderas, we monitor them. We are not expecting any of them to do this thing tonight. But the geological record is unambiguous. Eruptions like Toba have happened, and they will happen again, somewhere on Earth, on a timescale of tens of thousands of years. The record has a rhythm, and we are alive inside it. But we are not here tonight to predict. We are here to think slowly and carefully and quietly about one specific morning, one specific place, one specific wound in the planet, and what the wound has to tell us about the kind of species that survived it. There is something else worth saying before we begin. 74,000 years is not, by the standards of the Earth, a long time. The planet is 4.5 billion years old. The continents have been in motion for about 3 billion of those years. Life has been present for close to all of it. By geological reckoning, Toba happened yesterday afternoon. It is one of the most recent, genuinely huge things that has happened on the surface of this world, and it is the last of them that a member of our species could, in principle, have observed. That matters. That is why this story has a particular weight. Most of the great catastrophes we discuss on programs like this one, the ones that ended dinosaurs and changed oceans and remade continents, happened so long ago that they are stories of a different planet. Toba is a story of this planet, our planet, the one where there were already modern humans, anatomically indistinguishable from us, walking through the grasslands of East Africa and along the shores of the Arabian Peninsula. They were, in a real sense, us. They had our hands, our skulls, our voices. Whatever they experienced of that morning, they experienced with a body and a brain that, if you could meet them tonight, you would recognize as your own. So this is not deep time. This is near time. This is the morning when, by the best reconstruction science can give us, the world of our kind nearly came apart, or very nearly did not, or did something in between that we are still trying to understand. If you are going to sleep as you listen to this, it is all right. The story keeps itself. The ash does not need a witness to be counted. The sulfate is still in the ice. The lake is still in Sumatra. And your body is still, in some small, measurable way, the inheritance of a morning that none of your ancestors remembered clearly enough to pass the memory on. They passed something else on. They passed on the fact of their survival. That is what you are, a survivor of a morning whose story the ash will tell. To understand what the ash will tell, we first need to understand where the ash came from. Not the mountain alone, which existed briefly on a specific morning and then was gone, but the place, the geography of the place, the reason that, of all the points on Earth where a supervolcano could conceivably erupt, this particular stretch of Sumatra became the site of one of the largest explosive events in the last 2.5 million years. Sumatra is a long island. It is one of the 4 largest islands of the Indonesian archipelago, oriented northwest to southeast, shaped like a slightly curved knife. Along its spine runs a chain of volcanoes that has been more or less continuously active for most of the geological history of the Quaternary. There are dozens of them. Most are small. Some have erupted in historical memory, with names that have entered the broader vocabulary of Earth science. Krakatau, which is really a complex of islands in the Sunda Strait between Sumatra and Java, has erupted repeatedly, most famously in 1883. Sinabung, further north, is erupting now. Merapi, on neighbouring Java, is one of the most active volcanoes on the planet. They are all the product of the same geological fact. Underneath them, invisible, is a trench. The trench is called the Sunda Trench, and it runs parallel to the western coast of Sumatra at a depth of up to 7 kilometers below sea level. At the bottom of the trench, the floor of the Indian Ocean slides at a rate of a few centimeters a year under the edge of the Southeast Asian continental plate. The sliding is not smooth. It sticks. It releases. When it releases catastrophically, it produces earthquakes of the kind that remade the coastline of the Indian Ocean in December of 2004. That earthquake and its resulting tsunami killed more than 200,000 people. It happened because the Sunda Trench is alive. But the earthquakes are only one expression of what the trench is doing. Another expression, slower, more hidden, is the slow cooking of the ocean floor as it sinks into the hot rock of the mantle underneath. As the slab descends, it drags water down with it. Seafloor rock is hydrated. It carries the sea in its mineral structure. And water, when it is forced deep into the hot interior of the planet, does something unexpected. It lowers the melting temperature of the rock around it. The mantle above a subducting slab is already very hot, but the addition of water pushes parts of it past the melting point. Magma forms. The magma is lighter than the rock around it. It rises. When it reaches the base of the continental crust, it begins to pool. This is the engine. This is the slow machine that has built the Sunda volcanic arc, from the smallest cinder cones to the largest caldera on Earth. Every volcano you can see on a map of Indonesia is the top of a plume of magma that began its journey as subducted ocean floor. Every mountain is a story about water. At the place that would become Toba, this process had been running for a very long time. Bradley and colleagues, writing in 2016, described the particular geometry of the subduction beneath Sumatra as an example of diffuse deformation. What they meant is that the Indian Ocean lithosphere, the rigid upper layer that is being driven under the continent, does not behave as a single, clean slab. It buckles and partitions. It accommodates strain over a wide area. The result, beneath Sumatra, is a broad, low-angle subduction zone that feeds magma upward over a very wide region rather than concentrating it in a narrow axis. This allowed enormous volumes of magma to accumulate beneath Toba over the course of hundreds of thousands of years. There had been 3 previous Toba eruptions before the one we are thinking about tonight. The earliest known caldera in this complex formed about 1.2 million years ago. There was another at around 800,000 years. There was a third at around 500,000 years. Each of these was a major eruption. Each produced its own ash layer. Each collapsed its own mountain. Each left its own scar. And then, for approximately 400,000 years between the third and the fourth, the system was quiet. At the surface, anyway. From the viewpoint of a human being who could have walked through the forested plateau at any point during those 400,000 years, there would have been no mountain of any particular concern. The caldera of the third eruption would have been visible as a depression in the landscape, slowly being filled with sediment and overgrown with trees. The country would have looked like country. The rivers would have run. The animals would have moved. There would have been no reason to believe that anything unusual was gathering beneath the ground. But beneath the ground, unusually, something was. The magma chamber that would produce the Youngest Toba Tuff was not a single object. Petrological studies of the rock it produced indicate that at least 5 separate magma bodies were activated within a few centuries before the eruption. 5. Not one chamber slowly filling, but 5 distinct regions of melt, each with its own chemistry, rising through the crust and meeting. When they met, they interacted. They exchanged gases. They homogenized partially. They built pressure. What triggered the final release is not fully known. There are several candidates. One is that as the final magma bodies ascended, they reached a depth where the reduction in overlying pressure caused the dissolved volatiles in the melt, mostly water and carbon dioxide and sulfur, to come out of solution as bubbles. Bubbles in a magma are a problem. They make the melt expand. They can drive it toward the surface with explosive speed. Once a critical volume of bubbles forms in a chamber of this size, the chamber effectively fails. The roof fractures. The gas and the melt escape upward at velocities limited only by the speed of sound in the material. Another candidate is external. Sumatra is an earthquake country, in a way that few places on Earth are. Any sufficiently large tectonic event along the adjacent Sunda Trench could have perturbed the magma chamber, destabilized its roof, or sent a pressure wave through the melt that caused runaway vesiculation. We cannot know. The records that would tell us this, if they exist, are buried under 74,000 years of sediment and a 1,000-meter-deep lake. What we do know is the signature. The chemistry of the Youngest Toba Tuff is distinctive. Glass shards from the deposit, analyzed at the level of individual grains, carry a trace element fingerprint that is found nowhere else on Earth. Pierce and colleagues in 2014 used this fingerprint to confirm that every reported occurrence of Toba ash outside Indonesia, from the Arabian Sea to South Africa, belongs to this one eruption. Not to one of the earlier Toba events, not to some other Southeast Asian volcano, to this one. The morning. The 14-day window 74,000 years ago. The precision of this fingerprint is one of the great analytical achievements of quaternary volcanology. It means that when a researcher opens a core from the floor of the Indian Ocean and finds a thin layer of pale, glassy shards at a particular depth, she can hold that moment in her hand and know exactly when it happened. That layer is a timeline marker. It is what geologists call a chronohorizon. Chronohorizons are rare. They are the hairpin bends that allow scientists to pin widely separated records to a single moment. Toba is one of the best of them, which means that even though no human being alive today was there to witness the eruption, the event has become one of the most precisely dated natural events in the entire quaternary record. It is, paradoxically, a moment we can describe with more confidence than many events of the Middle Ages. And we can describe its place. The eruption happened at 2 degrees 41 minutes north latitude, 98 degrees 52 minutes east longitude, within 3 degrees of the equator. This matters. It is not a detail of mere geographic interest. The equatorial position of Toba meant that when the eruption column punched into the stratosphere, the sulfate aerosols it released were dispersed by tropical stratospheric circulation into both the northern and southern hemispheres. A volcano at high latitude would have affected only its own hemisphere. A volcano on the equator affects the entire planet. This is part of what makes Toba distinctive. It is part of why its climate consequences, whatever they were, reached as far as they did. The sulfate peak eventually deposited on the Greenland ice sheet at 75 degrees north, and the sulfate peak deposited on the Antarctic ice sheet at 75 degrees south are aligned to each other to within a handful of years. This would not be possible without an equatorial source. The eruption is physically documented in parallel at the 2 poles of the Earth because it happened in the middle. We will spend a later chapter inside those ice cores. For now, it is enough to hold this. The place of the eruption was a place whose atmosphere has access to the whole of the planet's sky. Whatever went up from that mountain in that 2-week window was fed into a global circulation. The stratospheric winds picked it up, the Hadley cells moved it, the polar vortices eventually pulled some of it down. The oceans, 40 or 50 years later, began to absorb the last of it. The eruption was local in its rock and global in its gas. One more thing before we leave the setup and watch the mountain go. The Toba region, even before the eruption, was already in the early stages of a climatic cooling. The broader Earth, 74,000 years ago, had begun its slide from the relatively warm interglacial of marine isotope stage 5 into the cold glacial of marine isotope stage 4. The transition had been underway for about 1,000 years. Global sea level was falling, northern hemisphere ice sheets were growing. Ocean temperatures had dropped by almost a degree. The planet, in other words, was already cooling. This matters because it will complicate every subsequent question about what Toba did. If the Earth was already cooling, how much of the cooling that followed the eruption was the eruption? How much was the ongoing glaciation? How much was both? This is the question that quaternary scientists have spent 3 decades arguing about. We will walk through the argument in its own time. For now, it is enough to stand for a moment longer on the forested plateau the morning before the eruption. The air is warm. The monsoon is blowing. The 5 magma bodies are already waking beneath us. The birds are calm. The island is as beautiful as the tropics always are. And none of this, in any reckoning we can recover, is going to last. 5 magmas were already waking. The magmas were waking. The column they produced would eventually reach the stratosphere, 32 kilometers up, and would blanket a fifth of the hemisphere in pumice and ash. But first, let us walk through the eruption itself, minute by minute, as far as the record will let us. Because the geometry of what happened is specific, and the specifics matter. The best reconstruction, pieced together from the thickness of the ignimbrite sheet, the composition of the glass shards, and the distribution of tephra across the Indian Ocean, is this. The eruption began with a comparatively modest airfall. A plume rose from a central vent. Ash and small pumice pieces fell around the mountain. For a short period, perhaps hours, this is what the eruption looked like. An impressive, but not unprecedented Plinian event. Something like Vesuvius in the year 79. Something local. Something unsettling if you were near it, ordinary if you were not. This did not last. The eruption transitioned quickly into its main phase. Pyroclastic flows. These are the slow, dense, lethal sheets of rock and gas that travel outward from the collapsing eruption column, hugging the ground, spreading radially around the vent. A pyroclastic flow is essentially a lava that is not liquid. It is a cloud of superheated pumice and shattered rock suspended in hot gas, and it moves, at its leading edge, at velocities of up to several hundred kilometers per hour. The temperature inside the flow is several hundred degrees Celsius. Nothing organic survives passage through one. For 9 to 14 days, pyroclastic flows poured out of the Toba caldera. That phrase requires a moment. 9 to 14 days. Not an instant, not a peak and decay event. A sustained, many-day release. Every hour for 2 weeks, the mountain that was no longer a mountain was generating flow after flow after flow, each one laying down its own layer of rock. By the end, the deposit was not a single unit, it was a stack. Inside the caldera itself, the stack is over 600 meters thick. In places outside the caldera, where the flows had to travel down the forested plateau and across the valleys of northern Sumatra, the deposit is about 100 meters thick, and it covers an area of 20 to 30,000 square kilometers. For comparison, 30,000 square kilometers is about the size of Belgium. Imagine a layer of hot rock, 100 meters deep, laid across the entire surface of Belgium over the course of 2 weeks. That is approximately the ignimbrite of the Youngest Toba Tuff. When a pyroclastic flow runs onto flat terrain, it spreads. It follows topography. It pours over cliffs and around hills. It does not, by itself, go up. But the gas that rises from its surface, full of buoyant, fine ash, does go up. This is what volcanologists call a co-ignimbrite cloud. Each pyroclastic flow, as it moves outward, is lofting a secondary column of lighter material into the atmosphere above it. The main eruption column of the Youngest Toba Tuff was, in this sense, not one column, but the integrated effect of many. Marty and colleagues in 2016, reconstructing the Toba plume from the distribution of the deposits, found plume heights between 22 and 35 kilometers. The upper end of that range is comfortably into the stratosphere. This is critical. To understand what the climate consequences of the eruption were, you have to understand that the ash and the gas did not stay in the troposphere, where rain and turbulence would have cleared them within weeks. They went higher. They crossed the tropopause. And once material is in the stratosphere, it stays there. Typical stratospheric residence times for volcanic sulfate aerosol are 1 to 3 years. Ash particles, which are heavier, clear more quickly, but the tiniest shards can drift for months. The climate effect of an eruption is, in a very real sense, a function of how high the column reached. Toba reached very high, 32 kilometers. That is the best current estimate for the ignimbrite column height, 32. For scale, the Pinatubo eruption of 1991, which is the largest stratospheric sulfate injection that modern satellites have ever measured, produced a column of about 35 kilometers, but for a single day. Toba produced a column of almost the same height, sustained for 2 weeks. This is the geometry of the event. Now, let us talk about the magnitude. The total volume of rock released by the Youngest Toba Tuff has been estimated several different ways. An early estimate put the figure at least 2,800 cubic kilometers. Of that, about 2,000 was ignimbrite, and 800 was the fallout ash that blanketed the surrounding region. More recent work, drawing on better coverage of outcrops and ocean cores, has revised the figure upward. The current best estimate, from Costa and colleagues in 2014, is 3,800 cubic kilometers of dense rock equivalent. Of this, about 1,800 fell as ash, and about 2,000 settled as ignimbrite. Older estimates have ranged as high as 6,000 cubic kilometers. 3,800 cubic kilometers is not an easy number to visualize. It is not a number that the human imagination handles well. One way to think of it, the total volume of water in Lake Superior, the largest lake in North America by surface area, is about 12,000 cubic kilometers. The Toba eruption released roughly a third of that volume, not as water, but as rock. Over 14 days, from a single caldera. Another way to think of it, if you took the ignimbrite alone and spread it evenly across the continental United States, the layer would be about 1/4 meter thick. 1/4 meter of rock over everything between New York and California. That is the ground deposit of the Toba eruption, transferred to a geography that did not actually receive it. And yet another way, Pinatubo in 1991 released about 10 cubic kilometers of dense rock equivalent, a VEI 6 event that caused a globally measurable temperature drop of 0.5 degrees Celsius for 2 years. Toba released 380 times that volume. The Tambora eruption in 1815, the largest historically observed volcanic event, which caused the so-called year without a summer in 1816, released about 100 cubic kilometers. Toba was 38 times larger than Tambora. These multipliers are not rhetorical. They are the raw input to every model that has ever tried to simulate what Toba did to the climate. They are the reason people have kept arguing about this event for 30 years. Let us pause in the 14th day. The flows have stopped. The column has collapsed. The air around the former mountain is opaque with ash and hot gas. The plateau is buried in rock so hot that it will still be warm in places for years. The sky is dark at midday. No animal is visible, no bird, no insect. The nearest living thing may be tens of kilometers away, on the far side of a ridge that the flows did not reach. The air is not breathable. The ground, in places, is hot enough to glow at night. And out beyond the edge of the flows, the ash is still falling. Ash from the Toba eruption reached the ground over an area of more than 38 million square kilometers. That is 7.5% of the entire surface area of the planet, at 1 centimeter or greater of thickness. The dispersal was not uniform. Prevailing upper-level winds drove most of the ash westward, which is why the thickest deposits outside Indonesia are in the Indian Ocean and the Indian subcontinent, not, for example, in Australia or in the Pacific. The monsoon circulation at the time appears to have pulled some of the fine ash southward into what is now the South China Sea, which is why deposits there, at 3.5 centimeters of thickness, are present despite being east of the volcano. On the central Indian Ocean basin, 10 centimeters. On the Arabian Sea, 1 millimeter, which is thinner but covers a very large area and is detectable in marine sediment cores wherever you drill. We have followed the ash in the intervening years all the way to the south coast of South Africa. We have found it in Lake Malawi in East Africa. We have found it in Lake Chala in Kenya. We have found it at sites in northwest Ethiopia that preserve Middle Stone Age archaeology. The ash, in other words, does what ash does when it is released at the equator in the summer monsoon. It goes almost everywhere, and it stays where it lands, and it waits for somebody, tens of thousands of years later, to come and find it. The fallen ash is a specific kind of material. It is a glass. Silicate glass with small amounts of crystals that did not have time to grow large before the melt chilled. Under a microscope, Toba ash looks like snowflakes made of volcanic glass, each shard a few tens of microns across, with delicate bubble walls and slivers of pumice. The chemistry of the shards is what makes them identifiable. There is potassium, there is silicon, there is a precise ratio of trace elements that other eruptions in the region do not match. If you find a layer of these shards in a core, you know what it is. And when the ash finally settled, the atmosphere did not immediately clear. The fine fraction stayed suspended for months. The sulfate aerosol stayed suspended for years. The sun was visibly dimmed. Measurements of how much it was dimmed and for how long are the central question of the next chapter. It is worth holding for a moment what this would have been like for a being standing at the edge of the ashfall zone. Say, a hominin in what is now central India, about 3,000 kilometers from the volcano. They would not have heard the eruption itself. 3,000 kilometers is well beyond the range at which even the loudest seismic acoustic events on this planet can be heard through the air. But they would have seen, within a few days, the sky change. First, it would have gone hazy, a brown haze, a thin grit in the wind. Then a finer, paler deposit would have begun to settle. By day 3 or 4, the ash would be visible on leaves, on the surface of water, on the skin of animals. By day 7 or 8, in central India, it would be 5 centimeters deep on every horizontal surface. The sun would have been rose-colored or orange, or a pale silver disk that you could look at without blinking. every breath would have carried the taste of glass. And this is only what happened 3,000 kilometers away. At 3,000 kilometers, the event is still only ash. What traveled farther, invisible, is what matters next. For now, this is the shape of the 14 days. A Plinian column, a transition to ignimbrite, pyroclastic flows hour after hour for 2 weeks. A co-ignimbrite column reaching 32 kilometers. 3,800 cubic kilometers of rock redistributed. 38 million square kilometers of ash. One mountain collapsed into a hole 100 kilometers long. One new landscape, still too hot to walk across, steaming and glowing in the dark. And above it, invisible, the column we cannot see. The sulfate, already rising, already spreading. The column we cannot see. The column we cannot see is what we will come back to. But let us, for this chapter, stay with the column we can. The ash. The part of the eruption that is still visible, still measurable, still locked into the sediment of lakes and sea floors across half the surface of the planet. The ash fell in layers. The thickness of the layer is a function of distance from the vent, of wind direction at the moment of deposition, of the particle sizes that remained aloft at each point along the trajectory, and of the geometry of the column that produced the cloud. Where a layer is thick, you have a lot of information. Where it is thin, you have less, but what you have is still decipherable, because even a fraction of a millimeter of ash preserves enough glass shards for a modern instrument to read them. The Indian subcontinent received the thickest distal deposit, 5 centimeters on average across a swathe that covered most of the peninsula. 5 centimeters is not a trivial layer. A footstep on fresh Toba ash would sink up to the ankle. Light rain would pack it down into a crust. A moderate rainstorm would wash it off the hillsides and into the rivers, and from there into the sea, where the suspended ash would settle out onto the continental shelf. In the deep sea sediment off the coast of Western India, this layer is still clearly visible today, 74,000 years later, as a pale band a few centimeters thick within the darker surrounding mud. It is the same ash, the same 14 days. The South China Sea received about 3.5 centimeters. This is one of the reasons we believe the eruption occurred in the northern summer. The summer monsoon blows the wind system that would have carried ash to the east-northeast to reach the South China Sea in that thickness. The rest of the year, the wind would have gone elsewhere. If the eruption had happened in northern winter, we would find thicker ash in the Indian Ocean south of the equator, not in the waters north of it. We find the opposite. So we know with reasonable confidence that this happened in the summer. In the central Indian Ocean basin, the layer is 10 centimeters thick. That is the single thickest distal deposit anywhere. It sits now beneath about 4 kilometers of seawater, buried under 74,000 years of subsequent pelagic sedimentation. Scientific drilling cores have recovered it. The ash at that depth is so well preserved that trace element analysis of individual shards matches, within analytical error, the chemistry of shards collected on the shore of Lake Malawi 9,000 kilometers away. Same eruption, same morning, same glass. This is why researchers call the Toba layer a chronohorizon. It is a timestamp that can be read in widely separated places with identical results. It is one of the most valuable stratigraphic markers in the entire Quaternary. The Arabian Sea received only about 1 millimeter. 1 millimeter is thin. It is easy to miss. But across the vast floor of the Arabian Sea, a millimeter of ash is still a great deal of ash in total mass, and the sediment cores that have been drilled there all contain the layer. Matthews and colleagues in 2012 used these ultra-distal deposits to demonstrate that the Toba ash, even at 1 millimeter thickness, carries enough identifiable shards to be securely attributed to the eruption. Everywhere the ash fell, it left evidence. This is the extent of the fall. In total, the surface area that received at least 1 centimeter of ash in the initial 2 weeks and the weeks following was more than 38 million square kilometers. 38 million square kilometers. That is about 7.5% of the surface area of the Earth. It is nearly the area of Africa. It is larger than Asia minus Russia. It is so large that the imagination has to work to hold it. If you were a bird at 30,000 feet flying westward from Sumatra a few days after the eruption began, you would have seen ash beneath you for the entire length of your flight, all the way to the coast of East Africa. You would have crossed the Indian Ocean and the Arabian Sea under a dust-dimmed sky. You would have come down onto a continent where the air still tasted faintly of sulfur, where the leaves of the acacia were gritty with silicate, where the sky at noon was not as bright as it should have been. And far beyond, where the ash was still settling in measurable quantities, the individual glass shards were still being carried by high-altitude wind. Microscopic Toba shards have been found in soil and lakebed cores on the south coast of South Africa. Pinnacle Point, a well-known archaeological site at the southern tip of the African continent, has Toba glass in its stratigraphy. Pinnacle Point is about 9,000 kilometers from Sumatra in a straight line. Ash from a volcano on one side of the Indian Ocean ended up at detectable concentrations on the coast opposite. This is the geographic envelope of the Youngest Toba Tuff. It is, by any honest reckoning, a hemispheric event. The shards tell their own story. Under a scanning electron microscope, Toba glass looks like a snowflake. The shards are angular. They have the feathery, delicate morphology of a liquid that cooled very quickly. Many are vesicular, meaning they contain small bubbles, frozen mid-formation. Their surfaces are smooth, their edges are sharp. Each one is a tiny monument to a specific process. The explosive decompression of a gas-rich rhyolitic melt, quenched to glass by adiabatic cooling in the eruption column. These shards are chemically distinctive. Toba glass is high in potassium, high in silicon, enriched in certain trace elements and deficient in others. The combination of major and trace elements produces a fingerprint that is, as Pierce and colleagues established in 2014, utterly unique to this specific eruption. Every reported occurrence of Toba ash outside Indonesia has been verified by electron microprobe to belong to the Youngest Toba Tuff, and not to any of the earlier Toba eruptions or to other Southeast Asian volcanic sources. This fingerprinting has been a scientific triumph. Before the technique matured, some researchers argued that a layer in East Africa labeled as Toba might actually come from a nearer volcano, or might be a blend from multiple events. The chemistry, read shard by shard, has ruled out the alternatives. The ash in Lake Malawi is Toba. The ash in the Gulf of Aden is Toba. The ash at Pinnacle Point is Toba. The ash in the Arabian Sea is Toba. All of it. All from the same 14 days in the summer of about 74,000 years ago. The oldest continuous record of the ash drilled up from the sea floor is the ocean drilling program Site 758 on the northern 90 East Ridge in the Indian Ocean. Dane and colleagues in 1991 worked through the neogene tephrochronology of this core, picking out volcanic layers from the entire history preserved in the sediment. The Youngest Toba Tuff appears there as one of the most prominent units, a pale band that jumps out of the grey-brown mud, recording the moment the Indian Ocean received its share of the eruption. This is how we reconstruct distant events. We drill, we look for layers, we look for the glass, we measure the chemistry. We date the sediments above and below, and from these fragments we assemble a picture of something that happened to a vast surface of the planet in a short period of time, long before anyone could have written it down. And some of what the ash tells us is surprising. For example, the timing of the eruption at the level of year or season. We know it was summer because of the South China Sea deposit. We know it was deposited over a period of perhaps months, with most of the material falling in the first few weeks. We know the wind fields at stratospheric levels were the ones you would expect for the summer monsoon. We do not, and probably never will, know the specific calendar date, because a calendar did not exist for this planet at this moment in any meaningful sense. But at the level of the month, we can triangulate. For another example, the ratio of ignimbrite to airfall. 2,000 cubic kilometers of ignimbrite, 1,800 of airfall. That ratio, about 11 parts ignimbrite to 10 parts airfall, is characteristic of a particular kind of eruption. It tells us that the column collapsed repeatedly and fed most of its mass into ground-hugging flows, rather than maintaining a single, sustained Plinian plume. Toba was, in this sense, less like a fountain and more like a very wide waterfall. And for a third, the sulfur. We said that ash is the visible column, the one we can see in the sedimentary record. The invisible column is made of gas, chiefly sulfur dioxide, which oxidizes in the stratosphere over weeks to form sulfuric acid droplets, which then hydrate and form the aerosol that has the climate effect. The quantity of sulfur released by the Toba eruption has been estimated several different ways, and the estimates disagree widely. Petrological constraints based on the sulfur content of melt inclusions in the preserved glass give a range from 10 to the 13th grams to 10 to the 15th grams. Ice core estimates, which measure the sulfate actually deposited on the polar ice sheets, give a figure of about 10 to the 14th grams, right in the middle of the petrological range. Costa and colleagues in 2014 modeled a delivery of 800 to 2,600 megatons of sulfate aerosol to the stratosphere over the 14-day period. This flux rate is unmatched in the Quaternary record. For context, the 1991 Pinatubo eruption released about 20 megatons of sulfur dioxide to the stratosphere, which produced an aerosol mass of about 30 megatons at peak. Pinatubo cooled the Earth by about half a degree Celsius for 2 years and remains the best observed volcanic aerosol event of the satellite era. Toba released, conservatively, 50 times that mass, and possibly several hundred times. Tui and Sigel, in 2017, placed the Toba aerosol optical depth, the measure of how much sunlight would have been scattered back to space, at the extreme upper end of any volcanic event reconstructible over the past 2,500 years. This is the sulfur. This is why the next chapter will be about what the sulfur did. There is one more point about the ash that should be named before we move on. The ash record, taken as a whole, contains more than the Youngest Toba Tuff. It contains every major volcanic eruption in Southeast Asia over the past 100,000 years. Bouvet de Maisonneuve and colleagues in 2019, using geochemistry of glass shards from multiple regional lakes and marine cores, identified at least 10 major eruptions in that window. Tambora, Krakatau, Rinjani, Somalis, others. All of them have left their own fingerprints in the sediment, each one smaller than Toba, each one a distinct layer, each one a reminder that this island arc is one of the most volcanically restless places on the planet. And yet none of those other eruptions, none, matches the Toba deposit in thickness, area, or aerosol load. Toba eclipses all of them combined. It is a genuine outlier, not just in the regional record, but in the global one. Its only true peers are events in deep geological time. The Oruanui eruption at Taupo, perhaps, or the Yellowstone eruptions of hundreds of thousands of years ago. Among eruptions close enough in time that modern humans could have been present to witness them, there is no second Toba. But first, this is the ash. This is the visible remnant. 74,000 years later, we still find it. We still read it. We still follow the trail from a caldera in Sumatra to a shore in South Africa, from the Arabian Sea to the South China Sea, to the drill cores on the 90 East Ridge. A fingerprint in glass, preserved by the indifference of geological time. The sulfur was the story.
So after the ash fell, what remained? This is a reasonable question, a fair one. An event of this magnitude does not leave its point of origin untouched. What remained in the case of Toba was a hole. The hole was the caldera, which is the technical term for the depression left when a volcano's magma chamber empties and the roof above it collapses inward. Calderas are common features on Earth. They range from a few hundred meters across to the dimensions of a small country. They are, in a sense, the negative space of eruptions, the shape of what is missing. The caldera at Toba is 100 kilometers long and 30 kilometers wide. When people say Toba is the largest quaternary caldera on Earth, that is what they mean. A hole large enough to hold the entire city of Los Angeles with room to spare. A hole large enough to see from orbit without magnification. A hole that altered the surface topography of northern Sumatra in a single 14-day event, to an extent that has not been undone in the 74,000 years since. The walls of the caldera, where they are preserved, rise steeply from the lake. On the western side, they are softer, more weathered, more gradual, because those slopes have been exposed to the monsoon for tens of thousands of years. On the eastern side, the walls are more vertical, still bearing the sharp geometric signatures of the original collapse. The ignimbrite inside the caldera, in places, is over 600 meters thick. A rock sheet, almost a kilometer of vertical stack, laid down in a 2-week window. After the collapse, the caldera did not stay a hole. It filled. The filling was slow. Rivers draining the highland plateau around the caldera delivered sediment. Rainfall, seasonal and monsoonal, added fresh water. The caldera floor, which was still cooling from the eruption, gradually stabilized. Over the course of the next several centuries to millennia, the whole became a lake. The lake is called Lake Toba. It is the largest volcanic lake in the world. Its surface area is 1,130 square kilometers, which makes it larger than the country of Singapore. Its maximum depth is around 500 meters, though most of it is shallower. Its outlet flows through the Asahan River, which runs east across Sumatra and empties into the Malacca Strait. The water in the lake is relatively fresh, with a slightly alkaline chemistry that reflects the surrounding volcanic geology. Fish live there. Boats move across its surface. It is, in every measurable sense, a functioning body of water, indistinguishable to the casual observer from any other highland lake on the planet. Except that this one is a scar. At the center of the lake, almost exactly in the middle, is an island. The island is called Samosir. It is roughly 650 square kilometers in area, which makes it about as large as the island of Singapore. A whole island inside a lake, inside a hole left by an exploded volcano. The nesting of these forms has a particular visual effect when you see it on a map. It looks, honestly, unlikely. It looks as if the mapmaker made a mistake. Samosir is not a mistake. Samosir is a resurgent dome. After the initial eruption and caldera collapse, the magma system beneath the caldera was not dead. A great deal of magma had been removed, but the lower crust and the mantle underneath continued to generate new melt. This new melt pushed upward against the floor of the caldera, slowly raising a block of rock from beneath the lake. Over the course of the last 74,000 years, this block has risen hundreds of meters above the surrounding lake floor. Its top now stands well above the water surface. It is effectively a volcanic uplift from below, dressed in forest and villages and fields. The people who live on Samosir today live on top of a slowly rising mass of crust that is still, in some measured sense, responding to the event that made the lake. This is what a caldera does when it does not stay dead. It breathes. Not rapidly, not in a way that would be dangerous to the living, but the resurgent dome of Samosir has risen, by the best geodetic estimates, a few centimeters per century. A rate that no human generation can perceive, but that, over geological time, produces the island as it stands. Alongside the resurgent dome, smaller features have formed. A cone called Pusuk Bukit rose on the southwestern margin of the caldera in the centuries after the main eruption. Lava domes pushed up elsewhere along the caldera walls, and on the northwestern edge, at a place called Tanduk Benua, there is evidence of an eruption so recent, perhaps within the last few hundred years, that the slopes around it have not yet been revegetated. The mountain, in other words, is not finished. The caldera has not gone to sleep. It is quieter than it was 74,000 years ago by many orders of magnitude, but it is not gone. This is a common property of large calderas. They remain weakly active for very long periods after their main event. Yellowstone in the American West has done this for hundreds of thousands of years. Campi Flegrei in Italy has done it for tens of thousands. Toba is in this same category. A major pulse, followed by a long, slow relaxation,
punctuated by small eruptions that are trivial compared to the parent event, but that remind us the system is still connected to its source. Toba today is a UNESCO Global Geopark. The designation was conferred in 2020, acknowledging the scientific significance of the site, the quality of its preservation, and its importance for research into both volcanology and the interaction between eruptions and human history. The Geopark designation comes with obligations. The lake and its surroundings are now formally protected, with research priorities, education programs, and heritage protocols that did not exist before. Tourists can visit. There are boat cruises. There are overlooks on the Caldera rim where you can stand and look down at the lake and try to hold in your head the size of what you are seeing. People have lived at Lake Toba for a long time. The Batak people, whose several related ethnic groups have inhabited northern Sumatra for centuries, make the caldera and its surroundings their cultural heartland. Their traditional stone houses, with the distinctive curved roofs that rise at each end, stand along the lake shore. Their music, their language, their foodways, all of them have developed in the shadow of the lake without, for most of that history, any awareness that the lake itself was the scar of an eruption that nearly ended their own species. This is worth sitting with. Human cultures have built entire identities around landscapes whose origins they did not, until very recently, understand. The relationship between a people and a place is often older than the scientific story of how the place came to be. The Batak of Samosir have their own stories about the origin of the lake, folk accounts involving a fisherman and a golden fish and a deluge. Those stories are older than the theory of plate tectonics. They are older than the word caldera, and they are, in their own way, as true as any scientific explanation, because they are about what it is like to live on an island inside a lake that no one made. The broader Toba region, 74,000 years ago, would have looked very different from what it is now. The immediate aftermath of the eruption, as we have said, was a landscape of hot ignimbrite still glowing at night, a steaming plain 200 kilometers across. It would have taken years, perhaps decades, for the surface temperature to drop to something survivable. It would have taken centuries for vegetation to return. And the return was not a simple restoration. Many of the plant species that had grown on the pre-eruption plateau were now locally extinct. The recovering forest was built from seed dispersal from beyond the affected zone, from birds carrying seeds, from wind-transported plant fragments, from whatever life had survived at the edges of the deposit. A different forest grew back than the one that had been there. This is, incidentally, the pattern seen after every very large eruption. Mount St. Helens, at a vastly smaller scale, followed the same trajectory. Krakatau did. The biological recovery zone is always a place where the new community is genetically and ecologically distinct from the old. At Toba, the process had more than 70,000 years to run. By now, the recovery is complete. The caldera walls are forested. The lake supports fisheries. The resurgent dome is covered with villages and farmland. The larger region produces coffee, rice, rubber, palm oil. It has the textured, lived-in, human character of any long-inhabited landscape in the Indonesian tropics. If you flew in tonight, you would see a beautiful highland lake. You would not, unprompted, see a scar. But the scar is there. It is the shape of the lake. It is the island in the middle. It is the two parallel geological facts. The volcano collapsed, and the collapse has not yet recovered. What looks like a placid body of water ringed by mountains is actually the most recent expression of a system that 4 times in the last 1.25 million years has emptied itself into the sky. There is one more thing that the setting gives us before we leave it and look up at the air. The sea level, 74,000 years ago, was falling. The transition from marine isotope stage 5 to marine isotope stage 4 was underway, which meant ice was accumulating at high latitudes and water was being pulled out of the ocean. By the time of the eruption, sea level was about 60 meters below modern. The coastlines of the Malay Peninsula, Sumatra, Java and Borneo were very different from today. They were connected. The whole region was a sort of super-peninsula, sometimes called Sundaland, extending southeast from continental Asia as a single landmass. The seas between these modern islands, when they existed at all, were narrow and shallow. This matters for the eruption's reach. The ignimbrite flows that reached the coast did not reach a deep ocean. They reached shallow seas, estuaries, coastal plains. In many places, the deposit probably poured across low-lying land and well out to sea before quenching. The outflow sheet likely crossed into the Indian Ocean and the Straits of Malacca, which would have been narrower and shallower than they are now. It also matters for what was living in the region. Sundaland was not empty. It was a forested landscape, a mosaic of tropical lowland and montane environments, carrying a dense and complex biota, including some of the last remaining populations of various archaic human lineages, who we will discuss properly in a later chapter. The eruption hit the middle of that landscape. The biological cost in the immediate radius of the pyroclastic flows was unambiguous and total. Nothing in that zone survived. But in the next chapter, we return to the thing we cannot see, the aerosol above the ash, invisible to any witness on the ground, that was still, weeks after the eruption ended, spreading silently through the stratosphere above every continent on the planet. Above the water, in the air. Above the water, in the air, the eruption was still happening. Or rather, its most climatically significant product was still spreading: the sulfur. We said earlier that the visible column of the Toba eruption was the ash. The invisible column was the gas. The gas is what we are going to spend this chapter on, because the climate consequences of a super eruption are almost entirely about the gas, and the gas is not ash, and it is not a single thing, and it is not easy to explain. Let us begin with what a volcano emits. A typical large silicic volcano releases, at the moment of eruption, a mixture of water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, hydrochloric acid, and a range of trace species. In mass terms, water is the largest component. Carbon dioxide is next. Sulfur compounds are generally a few percent. The sulfur compounds are, for climate purposes, disproportionately important. The reason is stratospheric chemistry. When sulfur dioxide reaches the stratosphere, it does not stay sulfur dioxide. It oxidizes. In the presence of trace hydroxyl radicals over a timescale of weeks, sulfur dioxide is converted to sulfuric acid. Sulfuric acid, in the stratospheric environment, rapidly hydrates and forms small droplets of concentrated sulfate aerosol. These droplets are typically around 300 nanometers in radius. They are small enough to remain aloft for a year or more, held up by their own Brownian motion and the slow sinking rates that apply to particles of that size. They are large enough to efficiently scatter incoming solar radiation, especially at visible and near-infrared wavelengths. The effect on the ground is that a lot of the light that should have reached the surface never gets there. It is scattered back to space by the aerosol. The planet cools. How much the planet cools depends on how much sulfur was injected, how high the injection reached, how long the aerosol residence time is, and what the background climate is doing. For the smaller eruptions of the last century, the relationship is well characterized. Pinatubo, 1991. 20 megatons of sulfur dioxide, peak cooling of about ½ degree Celsius, return to baseline in about 3 years. El Chichon, 1982. 7 megatons, cooling of about ¼ degree. Krakatau, 1883, estimated 30 megatons. Cooling effect unclear because we did not have satellites. Now we try to scale up.
To Tambora, in 1815, we attribute perhaps 100 megatons of sulfate and a global cooling of about ½ degree, with regionally much stronger effects, including the year without a summer of 1816 that killed crops across North America and Europe. To supereruptions like Toba, we attribute vastly more. But here the scaling breaks down. It breaks down because of what happens to the aerosol when there is too much of it. When you inject a very large sulfur load into the stratosphere in a short time, the sulfate droplets, initially small, begin to coagulate. They collide with each other, they grow, and larger droplets do two things that undercut the cooling effect. First, they scatter light less efficiently per unit mass, because the scattering cross-section does not scale linearly with particle size. Second, they fall out of the stratosphere faster. A droplet of 300 nanometers can stay aloft for a year. A droplet of 1 micron falls out in months. So if you double the sulfur injection, you do not double the cooling. In the limit, you may not increase the cooling at all. The aerosol self-limits. This self-limiting behavior is why the climate modeling of Toba has been, honestly, a mess. Different models, starting from different assumed aerosol sizes and different assumed residence times, arrive at dramatically different peak temperature anomalies. Early work from Rampino and Self, writing in Nature in 1992, argued for a severe multi-year volcanic winter with regional cooling of up to 10 degrees Celsius in some places and a global mean cooling of 3 to 5 degrees. That was the paper that made Toba a household name in climate science. It was also the paper that Ambrose, 6 years later, would use as the physical basis for his human bottleneck theory. But more recent modeling, using improved understandings of aerosol microphysics, is more conservative. Simulations by the Community Earth System model, using sulfur injections of 10 to the 14th grams and 10 to the 15th grams, produce maximum global mean cooling of 2.3 degrees and 4.1 degrees respectively, with recovery to within 1 degree of baseline within 3 to 6 years. A higher injection scenario, using 8.5 times 10 to the 14th grams, which is about 100 times Pinatubo, produces a maximum global cooling of 3.5 degrees and a recovery within 5 years. And the most recent empirical work on aerosol microphysics, informed by the very large sulfate injections from El Chichon and Pinatubo, suggests that the self-limiting effect may be severe enough that the cooling from an eruption like Toba might actually be limited to less than 1.5 degrees, regardless of how much sulfur was emitted. In this view, the eruption was huge, but its climate fingerprint was moderate and short-lived. This is the range of estimates we have. Anywhere from under 1.5 degrees to 5 degrees of global cooling, and anywhere from 3 to 10 years of recovery, depending on which model you believe and what aerosol assumptions you make. To actually test these estimates, we need physical evidence. We need ice cores. Polar ice caps, especially at their interior divides, accumulate snow every year. Each year's snow contains microscopic samples of the atmosphere above it, including trapped aerosols that fell out of the sky during the year. As the snow is buried by subsequent snowfalls, it compacts into ice, and the aerosol signature is preserved. Sulfate, in particular, can be measured to extraordinary precision in ice cores by ion chromatography. A large volcanic eruption shows up in the record as a sulfate spike, usually lasting 1 or 2 years. The spike can be dated by counting the annual layers above it, which are visible to the trained eye as alternating bands of lighter and darker ice reflecting summer and winter deposition. Greenland Ice Sheet Project 2, abbreviated GISP2, is one of the most famous ice cores ever drilled. In 1996, Zielinski and colleagues published a study of the GISP2 record covering the past 100,000 years. They identified a very large sulfate spike at approximately 71 to 73 kYr-BP, and on the basis of timing and magnitude, attributed it to the Toba mega-eruption. This was one of the earliest and most influential pieces of evidence placing the eruption inside the polar ice. In the intervening decades, more work has refined this. Svensson and colleagues in 2013 demonstrated that the Greenland and Antarctic ice cores could be directly synchronized at the Toba eruption, because both records contain a matching sulfate spike with identical shape and identical magnitude within analytical error. The northern and southern hemispheres, separated by thousands of kilometers and decoupled by the atmospheric Hadley circulation, nevertheless record the same event in the same way. This confirms the equatorial source. It confirms the stratospheric injection, and it provides one of the most precisely co-registered moments in the entire last 100,000 years of polar climate history. Svensson and colleagues updated this work in 2020, using bipolar synchronization to tie together abrupt climate change events across both ice caps. They placed the Toba sulfate event in the interval from 73.75 to 74.16 Kyr, with a sulfate loading among the largest ever identified in the Quaternary record. And here is the striking part. In the polar ice core records, the Greenland stadial cooling, known as GS20, a roughly millennium-long cold event in the North Atlantic, was already underway by the time the Toba sulfate was deposited. The cooling had started independently, some centuries before, driven by changes in Atlantic meridional overturning circulation. But immediately following the Toba sulfate deposition, there is a 110-year period of accelerated cooling. The authors interpret this as the Toba eruption intensifying an already ongoing climate transition, not initiating it, intensifying it. This is a more nuanced picture than the early Rampino and Self framing. It suggests that Toba did contribute to cooling, but against a background that was already cooling anyway, and the distinctive Toba fingerprint may be the acceleration rather than the initial shift. Related work by Tui and Sigel in 2017 synthesized the record of all volcanic sulfur injections identified in ice cores over the last 2,500 years, placing each of them on a common aerosol optical depth scale. Toba, when included on this scale, is at the extreme upper end, larger than any other identified event by a factor of several. Tui and Sigel use this to argue that the aerosol optical depth, meaning the amount by which Toba's stratospheric aerosol dimmed the Sun, was among the most extreme atmospheric perturbations that the Earth's climate system has experienced since the end of the Pleistocene ice cycles. Majewski and colleagues, writing in 1997, went further back. They synthesized the entire JISP-2 chemistry record for the past 110,000 years and demonstrated that Toba was among the dominant forcings on high-latitude atmospheric circulation across the record. It shows up as one of the biggest sulfate events. It shows up as a perturbation to the atmospheric chemistry of the Arctic. It is, in the polar record, not just visible, but conspicuous. And then there is the question of what the sulfur did to ozone. Ozone is the thin layer of O3 in the stratosphere that absorbs most of the ultraviolet radiation incoming from the Sun. Without it, UVB flux at the surface would be several times higher than it is. And it turns out that large sulfate injections, by providing surfaces for heterogeneous chlorine chemistry, can dramatically deplete stratospheric ozone over the tropics. Osipov and colleagues in 2021 modeled the ozone chemistry of Toba and concluded that the eruption caused severe tropical stratospheric ozone depletion. Severe enough in their model that the spectrum of ultraviolet radiation reaching the ground in the equatorial belt was altered for years. The world became briefly darker in some wavelengths, but harsher in others. This would have had direct biological consequences, especially for organisms near the surface in tropical latitudes. And the sulfate itself did not fall only on polar ice. Most of it, by mass, settled on tropical and temperate oceans and landscapes, where it is, by now, indistinguishable from the background sulfate budget. But the polar ice cores preserve it. The polar ice cores are what we read. Oppenheimer, in a 2011 review of sulfur degassing, pointed out that large silicic eruptions like Toba release most of their sulfur not from crystalline melt, but from a pre-existing supercritical fluid phase that had accumulated in the upper magma chamber over centuries. This is why the sulfur output can be so large relative to the volume of erupted rock. The sulfur was not dissolved in the melt. It was already gas-like before the eruption began, held under pressure. Baldini and colleagues in 2015 argued that this kind of explosive volcanism may have been a trigger, rather than a passive witness, of millennial-scale climate shifts during the last glacial period. Their proposed mechanism is that the cooling from large eruptions causes an expansion of sea ice, which shifts atmospheric and oceanic circulation patterns, which in turn trigger the abrupt climate transitions known as Dansgaard-Oeschger events. Whether or not Toba specifically triggered GS20, Baldini's work fits with the idea that very large eruptions are capable of perturbing the climate system in ways that go well beyond their immediate cooling effect. Free and Robock in 1999
provided a useful scaling. They showed that clustered VEI-6 eruptions can produce multi-decade cooling of around 0.5 degrees Celsius, as occurred during the Little Ice Age. Toba, at VEI-8, with 100 times the erupted volume, would be expected to produce a much larger effect. But as we have seen, the self-limiting aerosol physics may restrict the peak cooling to something like 2 or 3 degrees for a few years, rather than a multi-decadal ice age. So the honest summary is this. We know Toba injected an enormous quantity of sulfur into the stratosphere. We know some of that sulfur reached both polar ice caps and was preserved. We know a period of accelerated cooling followed the sulfate deposition in the Greenland record. We know from modeling that the global mean cooling was probably between 1.5 and 4 degrees Celsius and lasted a few years. We know the ozone chemistry was disrupted. We know the event occurred against a background climate that was already cooling for independent orbital reasons. And we know that at Lake Malawi in East Africa, not far downwind of where the ash fell, the sediment record does not show the signature of a volcanic winter at all. Yet the lake said nothing.
Not the ash, not the sulfate, not the model predictions. Not the assumption that because the eruption was enormous, the consequences must have been equally enormous. The physical evidence on the ground at one particular place in East Africa tells a different story. Lake Malawi is in Southeast Africa. It runs along the western edge of the East African Rift System, a long, narrow body of fresh water nearly 600 kilometers long, with a surface area of about 29,000 square kilometers. It is old. The oldest lake waters preserved in its basin go back several million years. It holds one of the largest and most ecologically complex assemblages of freshwater fish on Earth, hundreds of cichlid species, each evolved to a particular niche. It is a famous lake among biologists, and because it is old and its sediments are laminated and thick, it is also a remarkable paleoclimate archive. If you drill a core into the bottom of Lake Malawi, you can recover hundreds of thousands of years of annual or subdecadal environmental history, preserved in the alternation of fine detrital layers. You can count varves. You can identify pollen. You can measure stable isotopes of oxygen to reconstruct rainfall. You can identify microscopic phytoliths from grasses and other plants to reconstruct vegetation. You can date charcoal particles to track fire history. Lake Malawi is, in short, one of the best natural recorders of East African climate that we have. And Lake Malawi received ash from the Toba eruption. Christine Lane and colleagues, publishing in the Proceedings of the National Academy of Sciences in 2013, identified the Toba ash in a core from Lake Malawi. They were then able to examine in detail the environmental signal above and below the layer. Crucially, their sampling resolution was very high, essentially subdecadal in the relevant interval, so they could detect cooling or drying signatures that would have occurred on the timescale of the proposed volcanic winter, between 5 and 10 years. What they found in Lake Malawi is that there is no volcanic winter. The lake ecology shows no detectable change across the ash layer. The algae species composition, which is sensitive to temperature and nutrient supply, does not shift. The surrounding grassy woodlands, reconstructed from pollen, do not die back. The lake levels do not drop noticeably. In the decade after the Toba eruption, Lake Malawi continues to behave almost exactly as it had the decade before. Lane and colleagues concluded from this that the environmental effects of the Toba eruption in East Africa were either very mild or they were restricted to a period so short that even their sub-decadal sampling could not catch them. A volcanic winter lasting 5 to 10 years, of the kind that Rampino and Self had originally proposed, would have left a signature in Lake Malawi. There is no signature. A related study by Chad Yost and colleagues in 2018 went further. Yost's team analysed phytolith and charcoal records from the same Lake Malawi sediment at still higher temporal resolution. Phytoliths are microscopic silica bodies produced by plants, which are distinctive to particular plant taxa and survive in sediment. Charcoal tracks fire. Together, these two records capture the terrestrial response to climate, which is the part of the Earth system most sensitive to short, sharp, cold events. Yost's finding was that the phytolith and charcoal record across the Toba ash layer is nearly invisible. There are small shifts within the range of normal interannual variability, but there is no signature that would indicate a sustained cooling or drying event on the scale that global climate models of a 6 to 10-year volcanic winter would require. Yost concluded that the Toba supereruption had minimal effect on the vegetation of the Lake Malawi catchment over years to decades. This is remarkable. This is a major piece of physical evidence that whatever Toba did globally, at one specific place with excellent preservation, the signal is small. Of course, Lake Malawi is not the whole of East Africa, and it is not the whole of the world. It is one lake in a particular climatic and geographic position. But Lane and colleagues argued, and many others have since agreed, that if the volcanic winter hypothesis in its original strong form were correct, Malawi would have recorded it, and it did not. There have been rebuttals. One line of argument is that sediment mixing within the lake core may have smoothed out any sharp, short-duration signal, making a 10-year cooling look like near-continuous baseline. Another argument is that Lake Malawi is, as a tropical lake in a continental interior, insulated from the kind of sea ice-driven cooling that might have been the dominant mode of Toba climate forcing. And another is simply that one lake is not a global inventory, and there may be places where the cooling was sharper that we have not yet cored. But the Malawi result is hard to dismiss. It sits in the record. It says, in effect, at this one place, nothing much happened. Contrast this with a very different picture from Ethiopia. Martin Ziegler and colleagues, publishing in Nature in 2013, reported on a Middle Stone Age archaeological site in the lowlands of northwest Ethiopia, where Toba ash is preserved in a stratigraphic sequence alongside evidence of human occupation. Unlike the Lake Malawi result, the Ethiopian site does show a climate signal across the ash layer. The record shows a severe drought that began at the time of the Toba deposition and persisted for some period afterward. The drought was severe enough that it altered the foraging behavior of the humans at the site. They shifted their dietary strategy. They adjusted their hunting patterns.
Ziegler's interpretation is that the Toba eruption, whatever it did globally, did have a measurable regional impact in East Africa, at least at this specific locality. The impact was not a simple volcanic winter of global uniform cooling. It was a regional drought, probably driven by shifts in the East African monsoon rainfall belt that in turn were driven by changes in sea surface temperatures in the Indian Ocean. This is the actual picture, apparently. Not a single global cooling signature visible everywhere. Not a complete absence of signal. A patchy, regionally variable response, with some sites showing strong effects and others showing almost none. The climate modelers have, in fact, been predicting this for some time. The heterogeneity of the temperature and precipitation response to a very large stratospheric sulfate injection is itself a model prediction. The aerosol is global, but the response is regional, because atmospheric and oceanic circulation patterns determine how the cooling actually manifests in temperature and rainfall at any given latitude and longitude. Some places cool a lot, some places barely cool at all, some places get dry, some places get wet. Predicting which is exactly the thing climate models struggle with, and the Toba response is, in this sense, a natural experiment whose results are still being interpreted. The Lake Malawi result, in the global sweep of the argument, is one of the strongest pieces of evidence against the strong form of the Toba catastrophe theory. The Ethiopian result is one of the strongest pieces of evidence in favor of at least a regional Toba impact on human-occupied landscapes. The two results are not contradictory. They are regional variations of the same underlying global event. Greenland Stadial 20, incidentally, gives us the upper bound on what was possible. GS20 was a millennium-long cold event in the North Atlantic. It started at 74.0 to 74.2 Keir, which is almost exactly the time of the Toba eruption. It lasted about 1,500 years. It ended when Atlantic meridional overturning circulation re-established itself and warmth returned to the northern high latitudes. The question is, how much GS20 was Toba and how much GS20 was independent? The honest answer is that GS20 started, by the polar record, slightly before the Toba sulfate deposition. So it was not initiated by the eruption. But the eruption added to it. The 110-year accelerated cooling pulse that followed the Toba sulfate spike is likely the Toba signal within GS20, superimposed on the broader trend. The eruption amplified an existing cooling, it did not cause it. This is, in a certain sense, reassuring. It means that the climate system of 74,000 years ago was not unstable enough to be tipped permanently by a single eruption, however large. It means that most of the climate system returned to baseline within years to decades. It means that the long-term cold event that followed was predominantly orbital and oceanographic in origin, not volcanic. But it also means that for a few years the eruption did something. Somewhere between zero change in Malawi's phytoliths and multi-year severe drought in Ethiopia. And scaled up to the whole world, the integrated effect could have been substantial, even if no single site gives the complete picture. There is also the question of deforestation, which is an indirect but telling signal. Pollen records from India, reported in 2009 and summarized by Science Daily coverage of that work,
indicate prolonged loss of closed forest in the Indian subcontinent in the centuries after the eruption, replaced by open grassland. The deforestation happened over a scale of thousands of years, consistent with a combination of the eruption's immediate damage and the subsequent broader climate cooling. The forests of the Indian subcontinent were more directly hit by ash than almost any other region, and their recovery, as pollen records show, was slow. Related work by Cao and colleagues in 2005, studying dust chemistry over Asia, suggests that the way ash and aerosol interact with monsoon-driven dust regimes is complex enough that regional-scale simulations still struggle to reproduce observed phenomena. This is, again, a reminder that the Toba response was inhomogeneous across the planet and at a resolution we are still catching up to. So where do we stand on the climate chapter of this story? We stand here. The eruption was real. It was huge. It injected a globally unprecedented load of stratospheric sulfur, and it caused a real, if modest, global cooling. The cooling was regionally variable, strong in some places, nearly invisible in others. It lasted roughly years, perhaps a decade, before recovering. It occurred against a background of independently ongoing glacial onset cooling, which it amplified but did not create. And its combined effect on the biosphere was severe enough to deforest parts of southern Asia and cause droughts in East Africa, but not so severe as to leave a definitive, uniform signal in every climate archive. This is not the catastrophic volcanic winter of the 1992 Rampino Self hypothesis. It is not a completely benign event either. It is something in between, and the in-between is where the argument continues to live. Which raises the next question, because even if the climate shift was moderate at many sites, the human genetic record still shows a bottleneck. Something happened to our numbers around this time. If not the volcanic winter, then what? Did the eruption contribute indirectly through regional effects on foraging, migration, and disease? Did it coincide with some other demographic factor? Did we crash and then recover, leaving the genetic signature we see today? For these questions, we have to turn from the lake and the ice core to a much stranger archive: the human body, the human genome, the archaeological record of what our ancestors actually made and used in the centuries around the eruption. But the genomes still argue. We have asked what the lake did not say. Now let us ask what the genomes still argue. Because whatever happened to the climate, something happened to us. This is the uncomfortable, beautiful, contested part of the Toba story. It is the part that made Toba famous outside of geology. It is the part that put Sumatra into newspaper headlines. And it is the part where the science is most difficult to settle. The story begins, oddly, in 1972. A published analysis of human hemoglobin variants drawn from many individuals across many populations counted the number of distinct variants in the molecules of their red blood cells. The number was small, very small, smaller than it should have been if the human population had been breeding at its modern size for very long. This is a specific kind of analysis. What it tells you is not directly the census population,
which is the total number of people walking around at any given moment, but the effective population, which is a more abstract quantity. The effective population is something like the breeding population averaged over time, and it is what determines the rate at which genetic variation accumulates or disappears. A small, effective population produces a narrow gene pool. A large, effective population produces a broad one. The analysis, and later work that followed, indicated that the human effective population size for most of our history has been in the range of 10,000. 10,000. Not the billions you see on the globe today. 10,000 breeding individuals scattered across the landmass, producing the genetic ancestors of every human alive today. Subsequent studies through the 1980s and 1990s confirmed and refined this. Mitochondrial DNA sequences were compared across populations and used, through what geneticists call coalescence analysis, to date the most recent common ancestor of the mitochondrial lineage. The answer that emerged was that our most recent matrilineal common ancestor, sometimes called mitochondrial Eve, lived around 150 to 200,000 years ago in Africa. Between that time and the population explosion of the Holocene, the effective human population remained very small. There is a period in particular where it appears to have been as low as 1 to 10,000 individuals, before it began to grow rapidly somewhere between 35,000 and 65,000 years ago. Among these numbers, the minimum is the notable one. 1,000 breeding individuals, a few thousand breeding pairs. That is the flaw that emerges from the genetic record. And the timing of that flaw, the window where the human gene pool was at its narrowest, overlaps, somewhat roughly, with the timing of the Toba eruption. In 1993, the science journalist Anne Gibbons wrote about the emerging paleoanthropological consensus that the Pleistocene ice ages had suppressed human populations. She suggested, as a hypothesis for discussion, that the Toba supereruption, then dated to roughly 73 to 75 Keir, might have contributed to this suppression. It was an aside. It was one paragraph in a longer argument. But it caught the attention of the right people. Those people were Michael Rampino and Stephen Self. Together, they developed the volcanic winter hypothesis that we discussed 2 chapters ago. And in 1998, the anthropologist Stanley Ambrose, drawing on both the genetic data and the Rampino-Self climate model, published a paper in the Journal of Human Evolution that formalized what became known as the Toba catastrophe theory. Ambrose's argument was as follows. A severe, multi-year volcanic winter following the Toba eruption would have caused a collapse of human populations everywhere, but especially in the high latitudes and in inland continental areas with marginal food security. The survivors would have been reduced to a few thousand individuals worldwide. This would have imprinted a bottleneck in the human gene pool, which is what we see in the mitochondrial and later whole genome data. The eruption, Ambrose argued, was the near-extinction event of Homo sapiens. This is a striking story. It is a story that, once stated, is impossible to forget. It packages a vast geological event, a specific human fate, and a dramatic narrative into a single hypothesis. It is, in its best form,
the kind of thing that makes science captivating to non-scientists. It is also, as we have now seen, not a settled theory. The Lake Malawi evidence from Chapter 7 pushed back against the volcanic winter side of the argument. The Indian archaeology pushes back on the human crash side. The site that does this most dramatically is in the Juraru Valley of southern India, where Michael Petralia and colleagues, working across multiple excavation seasons, have documented stone tool assemblages in stratigraphy above and below the Toba ash. The Toba ash at the Juraru site is a centimeters-thick layer of pale tephra deposited 74,000 years ago, sitting within an otherwise continuous archaeological sequence. Middle Paleolithic Levallois-style flakes are found below the ash. Middle Paleolithic Levallois-style flakes are found above the ash. The assemblages are, by Petralia's analysis, very similar across the layer. The same technology, the same use patterns, the same basic pattern of human behavior. This is not what a catastrophic local population collapse should look like. If the people of the Juraru Valley had been wiped out by the eruption and the site had later been reoccupied by genetically distinct survivors from elsewhere, you would expect to see a discontinuity in the stone tools. You might see a long period of abandonment. You might see a different tool-making tradition. You might see no continuity at all. You see continuity. Petralia and colleagues published this argument in Science in 2007. The science blogger John Hawkes, writing the same year, called it the death of the Toba bottleneck. The phrase was memorable and it got quoted, but Hawkes was careful in the broader context to note that this single site does not kill the entire bottleneck hypothesis. It does, however, complicate the simplest version of it. At the Juraru Valley site, optically stimulated luminescence dating puts the tools below the Toba ash at 77 plus or minus 4 Kehr. The tools above the ash are younger, but dating them more precisely is difficult, and they are constrained to be no older than 55 Kehr. This leaves an age gap of over 20,000 years. One interpretation is that the gap reflects removal of post-eruption sediment by erosion. Another is that the local population did, after all, crash and take many millennia to recover. Yet another is that the site was abandoned and reoccupied by a later wave of immigrants from elsewhere. We do not have enough evidence to pick between these. Additionally, other sites across India have been compared to Juraru. Some show apparent continuity. Others, like Middle Sun Valley in Madhya Pradesh, show evidence of a major decline. Juraru may have been protected by its abundant springs, which could have provided fresh water when surface water bodies were disrupted by the eruption. Different local geographies may have produced different local outcomes. This regional variability is increasingly the picture. Just as the climate response was patchy, the demographic response was patchy. Some communities rode out the eruption with little apparent change. Others suffered badly. Let us step back from India and look at the global genetic picture again, using more recent methods. Whole genome sequence analysis, applied through hidden Markov model-based coalescence methods, allows researchers to reconstruct effective population size through time at much higher resolution than was possible from mitochondrial DNA alone. These modern methods recover a long, complex demographic history, not a single sharp event.
For non-African populations, the record shows a steep decline in effective population size starting around 200,000 years ago and reaching its lowest values around 40 to 60,000 years ago. During this bottleneck, non-African populations experienced a 5 to 15-fold reduction, dropping to an effective population size of only 1 to 3,000 individuals by 50,000 years ago. This severe contraction is consistent with a founder effect caused by the out-of-Africa dispersal. A small group, a few thousand strong, migrated from Africa into the Near East and from there to Eurasia and beyond. Their genetic diversity became the starting point for all non-African human diversity today. Within this decline, geneticists have identified a cluster of cold adaptation selective sweeps. 56 independent sweeps have been detected in non-African populations, of which 31 occurred between 72 and 97 KYR. This cluster has been named the Arabian Standstill. It suggests that during this period, non-African human populations underwent rapid selection for cold-adapted traits against a background of severe cold and aridity that would have characterized the onset of marine isotope stage 4, possibly exacerbated by the Toba eruption. For African populations, the demographic picture is different. African populations experienced a slightly earlier, milder bottleneck and recovered earlier. Samples from the Luya and Maasai peoples of East Africa reached their lowest effective population sizes around 70 to 80,000 years ago. Samples from the Yoruba people of West Africa reach a nadir closer to 50,000 years ago. African effective population sizes during these troughs were around 10,000 individuals, substantially larger than the non-African figure of 1 to 3,000.
This is consistent with the observation that the modern human gene pool is most diverse in Africa. Africans carry genetic variation that the out-of-Africa migrants left behind. The migrants carried only a sampling of the parent diversity with them, and that sampling is what became the world's non-African genomes. Now, within this framework, where does Toba sit? Not as a single unambiguous cause. The timing of the deepest bottleneck, around 50 Kaya, is later than the Toba eruption at 74 Kaya. The African bottleneck is largely prior to Toba. The non-African bottleneck is partly concurrent with Toba and partly later. The cold adaptation sweeps of the Arabian Standstill overlap with the Toba window, but the climate forcing responsible for them may have been the glacial cycle in general rather than the eruption specifically. The most honest modern interpretation is that Toba occurred against the backdrop of a long, multi-cause demographic trough, possibly amplified the trough locally, contributed selection pressure in affected regions, and left its fingerprint somewhere in the deep architecture of the human population history, but was not in itself the cause of the near extinction some early proponents suggested. And other species show parallel patterns. Tigers, for example. Luo and colleagues in 2004 reported a phylogeography of tigers across Asia, showing that the most recent common mitochondrial ancestor of the 6 modern tiger subspecies lived approximately 72 to 108,000 years ago. That window overlaps with the Toba eruption. The tigers of Asia appear to have gone through a demographic bottleneck of their own, from which they began to diversify only after the event. This is not proof of Toba causation. It is suggestive. It indicates that at least one large mammal, sharing habitat with humans across southern Asia, went through the same kind of demographic event around the same time. Other human lineages also survived the eruption and the subsequent marine isotope Stage 4 Ice Age. The Neanderthals of Europe and Western Asia persisted until approximately 40,000 years ago. The Denisovans, known from DNA in a Siberian cave, persisted until around 55,000 years ago. Other archaic lineages in Indonesia and the Philippines were also still present when Toba erupted. None of them went extinct immediately because of the eruption. All of them survived to interact, in some cases genetically, with the Homo sapiens dispersal that would follow. This is an important point. Whatever Toba did to us, it did not eliminate our relatives. The other human lineages made it through. Their eventual extinctions, tens of thousands of years later, had other causes. La and Foley, in 1998, provided a framework for thinking about Homo sapiens as a structured meta-population in Africa, whose dispersals were shaped by Pleistocene climatic oscillations, including Toba. In their model, the small, effective population sizes we see in the genetic record are the integrated expression of many waves of local expansion and contraction, rather than single, catastrophic events. The Toba eruption, in this view, is one among many climate biological forcings, not the single bottleneck-making event that Ambrose 1998 proposed. The consensus among paleogeneticists today is closer to La and Foley than to Ambrose. Nobody doubts that the eruption was real and climatically significant. But the idea that Toba, specifically, crashed our species to a few thousand and nearly ended us is treated as an overstatement of a more complicated story. What did happen? Probably, the humans alive at the time of Toba, a few tens of thousands of them at most, were already living in small, dispersed, genetically structured populations. The eruption affected some regions severely, others barely at all. Some local populations declined, others moved. Some may have gone extinct. The global total effective population, which was already quite small, became marginally smaller. Subsequent climate cooling kept it small for tens of thousands of years. When conditions finally improved, around 30 to 40,000 years ago, the populations began to grow, and the grown population became, by sometime in the Holocene, the 7.5 billion people alive today. We are all descended from those few tens of thousands, all of us, every person alive. Our genetic diversity is the remaining diversity of what they carried. Our physical traits are drawn from the physical traits they had. Our language capacity, our tool-making capacity, our social structures, our longing for narrative, all of this is what they passed on. And the passing on was by no means guaranteed. At a few points, apparently, it was thin. The lineage nearly snapped. It did not snap. Here we are. Neanderthals were still alive.
Neanderthals were still alive 74,000 years ago. They were, when Toba erupted, living across most of Europe and Western Asia, hunting in forests and along riverbeds, making tools whose styles are distinctive enough that archaeologists can tell them apart from ours at a glance. They did not know a volcano had erupted 7,000 kilometers away. Their descendants would persist for another 30,000 years. And so, on a more ordinary note, what about now? What about Toba as it exists tonight, as you are listening to this in the early 21st century? The caldera is still there. That should be said first. The lake is still 100 kilometers long. The resurgent dome is still Samosir Island. The Batak villages are still along the shore. The highland climate is still cool and damp. The system, at the surface, has the aspect of a quiet and beautiful inland sea. But beneath the surface, the system is not inert. Small volcanic cones have built themselves on the margins of the caldera since the main eruption. Pusuk Bukit on the southwestern rim is one of them. It is a modest peak, not dramatic, a typical cinder cone of the kind that builds from a few episodes of local eruption over a few thousand years. It is one of the signatures of the slowly resurgent magma system beneath the caldera. At Tanduk Benua, on the northwestern rim, there are indications of a much more recent eruption. The slopes around Tanduk Benua lack the vegetation you would expect after tens of thousands of years of weathering. They look fresh. They look, by the standard of volcanology, young. Some analyses suggest the most recent eruption at Tanduk Benua happened within the last few hundred years, possibly within historical memory, though the event is not recorded in the written sources of the region. This is what a large caldera does when it is not done yet. It does not produce another supereruption on any timescale you would have to worry about in a human lifetime. Toba, in its pre-74,000 years ago rhythm, produced one caldera-forming eruption every 200,000 to 400,000 years. We are 74,000 years past the most recent. If the pattern held, we would have a very long time before the next one. Almost certainly, the timescale of the system is much longer than the timescale of our species, let alone our civilization. But small eruptions are another matter. Tanduk Benua, if it erupted within the last few centuries, is a reminder that the magmatic plumbing beneath Toba is still wired. Heat is still rising. Fluid is still migrating. The system is quiet, not dead. In 2020, UNESCO formally recognized the Toba caldera as a global geopark. The designation acknowledges the scientific significance of the location, the ongoing research into its geology and biology, and the role it plays in the cultural heritage of Indonesia. Global geopark status comes with obligations. The region is now managed under a protocol that balances tourism, research, and conservation. There are new educational centers. There are protected viewing points. There are coordination programs with Indonesian universities to ensure that ongoing research is integrated with local community interests. This matters for a reason that goes beyond tourism. Large caldera systems globally are understudied. We know a lot about active stratovolcanoes like Vesuvius or Etna or Popocatépetl because they erupt often enough that we can watch them. We know much less about calderas, which produce truly large eruptions on long recurrence intervals and, in between, sit quietly for hundreds of thousands of years. Toba, as a long, quiet caldera, is a natural laboratory for understanding what these systems do while they sleep.
The geopark designation protects and funds that understanding. The lake itself, meanwhile, is a living ecosystem, and it is under pressure. Haroon and colleagues in 2021 documented the ecological condition of Lake Toba and found that, while the lake remains biodiverse, it is significantly stressed by invasive species. In particular, water hyacinth, a fast-growing floating plant native to South America, has spread across parts of the littoral zone and, in some bays, blankets the water surface so thickly that sunlight cannot penetrate to the algae below. Fish populations have declined. Nutrient cycles have shifted. The lake, in other words, is undergoing the same sort of anthropogenically driven ecological change that affects most large lakes in the tropics. The cultural life around the lake has also changed. The Batak people, whose traditional villages and agricultural systems have thrived in this landscape for centuries, now participate, like everyone else, in a globalized economy. Some families still fish. Some still farm the volcanic soils, which are fertile enough to support coffee, rice, and a range of fruit.
Some work in hotels and tourist operations that serve visitors who have come to see the lake. The mix of subsistence traditions and modern commercial life, visible at any Sumatran market, is the texture of 21st century Toba. If you flew in tonight, you would land at a small regional airport called Silangit. You would drive up a winding road into the highlands. You would reach, eventually, the ridge of the Caldera and a viewpoint where the lake opens before you. The lake is so large that the far shore, on a clear day, is barely visible. The water is dark. The island of Samosir sits in the middle distance, forested and populated and quietly alive. The air is cool, always cooler than you would expect at this latitude because of the altitude of the Caldera rim. You would have no reason to think, standing on that ridge, that you were looking at the largest explosive eruption of the Quaternary. Nothing on the landscape tells you. The landscape is green. It is tranquil. It has the cultivated quality of long human residence. And yet, if you knew the geology, you could read it in the shape of the lake. 100-kilometer lake with an island in the middle, at the center of a volcanic island arc, is not a natural lake in any ordinary sense. Every geological feature of the place is either a remnant of the eruption or a response to it. The caldera walls are the edges of the collapsed chamber. The lake is the water that filled the hole. The island is the recovery of the magma system. The surrounding hills are the landscapes that once held the mountain. You are standing, effectively, inside a very large, healed wound. Comparing this to Tambora in 1815 is instructive. Tambora, in eastern Indonesia, erupted with a volcanic explosivity index of 7, which makes it the largest historically observed volcanic eruption. It released approximately 100 cubic kilometers of ejecta, which caused the famous Year Without a Summer of 1816 across the Northern Hemisphere. Crops failed in New England. Summer snow fell in upstate New York. Cold rain destroyed harvests across Europe. The ripple effects of Tambora are recorded in letters, diaries, newspaper articles, crop yield records, and climate reconstructions. We know what a VEI-7 eruption does to the world. Toba was 38 times larger. That scaling does not directly translate to 38 times the cooling. We have already seen that the aerosol self-limiting effect complicates the math. But even allowing for that limit, the cumulative effect of Toba on the global atmosphere was much greater than Tambora. Tambora left us with a cold year. Toba, whatever else it did, left us with a sulfate layer in the polar ice that dwarfs every other volcanic signal in the record. Bouvet de Maisonneuve and colleagues in 2019 compared the Youngest Toba Tuff to at least 10 other major Southeast Asian eruptions over the past 100,000 years. Krakatau, which is the eruption everyone knows, was on the order of tens of cubic kilometers in its 1883 paroxysm. Samalas, a massive 13th century eruption in Lombok that has been blamed for various climate anomalies, including the onset of the Little Ice Age, was similarly on the order of tens of cubic kilometers. Tambora, as we said, is 38 times smaller than Toba. Every single major Indonesian eruption of the last 100,000 years combined does not approach the scale of Toba. This is why Toba matters for the broader conversation about supervolcanoes. It is the best preserved, best studied example of a recent VEI-8 event. It is our reference case. And there are other supervolcanoes in other parts of the world that have produced eruptions of similar class in the geological past. The Yellowstone caldera in Wyoming, which produced a VEI-8 eruption around 640,000 years ago, and earlier events at 1.3 million and 2.1 million years ago. The Taupo volcanic zone in New Zealand, which produced the Oruanui eruption around 25,400 years ago. Campi Flegrei in Italy. Each of these has the potential, in geological time, to produce a Toba-class event again. None of them is showing current signs of imminent activity. The probability of any one of them going super-eruptive in the next century is very low. Modern volcano monitoring, especially the network maintained by the United States Geological Survey and by similar agencies in Japan, Italy, New Zealand and Indonesia, would almost certainly detect the multi-year precursor signals that such an event would generate. You would see ground deformation. You would see magma intrusion. You would see a distinct gas emission signature. We are not, tonight, on the edge of another Toba. But the system is not gone from the planet. Another supervolcanic eruption will happen, somewhere, at some point. The only uncertainty is where and when. On the scale of a human life, it is improbable. On the scale of civilization, it is likely, but not certain. On the scale of the species, it is almost inevitable. This is a sobering thought. It is also, in a way, a humble one. Our presence on the Earth has been short enough that no member of our species has ever witnessed a super-eruption with any kind of technological observation. The eruption that made Lake Toba was watched, if at all, by small groups of early modern humans who had no way to understand what they were seeing. The next one will, presumably, be watched by us through satellite imagery and ground sensors and open international data channels, and we will understand it at a level no witness has ever managed before. What we do with that understanding, and how we prepare, and what we learn, and how much of what we have built survives,
Those are the questions that a species with a science of volcanoes gets to ask itself. Our ancestors did not get to ask them. They had to survive the winter with only the skills their hands already held. And so we come back to that question, the quiet one. What did the winter teach us? Not the scientists, not the climate modelers, not the paleogeneticists, but us listening tonight, us alive today. The question of a lake in Sumatra is, in the last analysis, the question of a species looking at its own unlikely persistence. 200 generations of ancestors, give or take, separate us from the people who stood downwind of this eruption. 200 generations of survival. 200 generations of passing the body forward. What did the winter teach us?
What did the winter teach us? Let us be honest about what it taught us. It is a harder lesson than most because it is not a single lesson. It is, as everything about this story has been, layered. The first lesson is this. A civilization-ending event can happen to a species without the species going extinct. Toba happened. Our ancestors experienced it, or some of them did, or some of their neighbors did. Some populations collapsed, some communities vanished, some regions became uninhabitable for decades or centuries, and the species continued. It continued thinly. It continued through bottlenecks that are written into every cell of your body, but it continued. This is not a comforting lesson in the shallow sense. It does not say that your particular community will survive the next supereruption, whenever it comes. It does not say that your particular city will be spared. It says instead that the species has proven, once, that it can take a hit of this magnitude and still be here. What the lesson means for any individual is ambiguous. What it means for the aggregate human enterprise is that we are, if nothing else, stubborn. The second lesson is about evidence. 74,000 years is a long time by any reasonable standard, and yet the traces of Toba are still decipherable, still legible, still being refined as techniques improve. The ash in the Indian Ocean basin is still there. The sulfate in the polar ice is still there. The stone tools above and below the Juriru ash are still where Petralia and colleagues found them. The coalescence math on our mitochondrial DNA still points to a bottleneck. The Earth, for better or worse, has a long memory. Events of sufficient magnitude leave physical traces that we, given time and instruments, can read. This is an epistemic achievement that is easy to take for granted. The fact that we can stand here tonight and speak about a morning 74,000 years ago, with dates accurate to plus or minus 300 years, is the accumulated work of thousands of scientists over decades. It is a kind of memory that humans did not previously have access to. We can look backwards now into time we never witnessed, and sometimes, at a few remarkable moments, we can see. The third lesson is about uncertainty. We do not know, even after all this work, exactly what Toba did to us. We know it cooled the planet. We do not know by exactly how much. We know our genome shows a bottleneck. We do not know if the bottleneck is Toba's fault or the Pleistocene's fault, or the consequence of out-of-Africa migration, or some combination. We know some communities made it through. We do not know how many did not. The honest summary of everything in this documentary is that we are standing in a field where the questions are large and the evidence is partial and the answers are multiple. Some listeners encountering this find it frustrating. They want the clean story. They want Toba as Ambrose told it.
The Great Winter, the near extinction, the stark and simple image of our species reduced to a handful of survivors huddled around fires in a world gone dark. That story is a good story. Parts of it are probably true. Parts of it are probably false. The full picture is messier. But messiness in science is not failure. It is what the world actually looks like when you look closely. Simple stories are rhetorical constructs. They serve communication. They do not always serve truth. And Toba, like almost every other Pleistocene event of sufficient scale, is a topic where the simple story has been revised several times and will be revised again. This is not a flaw in the science. It is the science working as intended. The fourth lesson is about scale. 74,000 years is a short time by the standards of the planet. The Earth is 4.5 billion years old. Toba is the most recent of a series of events that have shaped our biosphere repeatedly across geological time. There have been bigger eruptions. There have been more extinction-producing events. The Permian end, the Cretaceous end, the Chicxulub impact. All of these dwarf Toba in every measurable way, and they did not happen in human time. Toba is a reminder that the Earth has not gone quiet just because we are here to watch. Snyder Beatty and colleagues in 2019 tried to estimate an upper bound on the background rate of human extinction from natural catastrophes. Using the fact that we have survived for some period of time and using events like Toba as calibrations for how severe catastrophes can get, they arrived at an upper bound of less than 1 chance in 87,000 per year. That is, of any given year, the probability that a purely natural event will end the human species is very low. Lower than most people intuitively guess. The number is not 0, but it is small. Of course, this does not bound the probability of civilizational collapse, which is much higher. A volcanic winter 3 or 4 degrees cooler than present, persisting for 5 years, would badly disrupt global agriculture and supply chains in the modern world. Billions of people now depend on food production systems that are finely tuned to the current climate. A multi-year stratospheric sulfate injection would test those systems severely. We would not go extinct. We would, however, face serious food insecurity and political crisis. This is the practical lesson of Toba for the present. The eruption, if it happened again somewhere tonight, would be a civilization-scale problem, not an extinction-scale one. The difference between those two outcomes is the difference between a species' capacity to adapt and its capacity to survive at all. Our ancestors, who faced Toba with nothing but stone tools and kinship networks, survived. Their capacity to adapt was their only asset. We, today, face a hypothetical future Toba with a vastly greater toolkit, and also with a vastly greater dependence on that toolkit to stay alive. Which of those factors wins, if tested, is an empirical question no one has data on. The fifth lesson is closer to home. Every person now alive carries within their cells the signature of an ancient bottleneck. Your mitochondrial DNA coalesces approximately to a woman who lived 150,000 years ago in Africa. Your Y chromosome, if you have one, coalesces to a man of similar antiquity. The small diversity of your genome, compared to the diversities of great apes,
reflects that your ancestors were few at some points in the past. This is a kind of intimate inheritance. It is not sentimental. It is a matter of record. When geneticists count the number of distinct variants in your HLA complex, or in your globin genes, or in your microsatellite repeats, the count is small. It is not small because you, as an individual, are unremarkable. It is small because your species, as a whole, passed through a narrow channel on its way to the present. You are the continuation of that passage. You are, in this quite literal sense, what survived. The sixth and last lesson, which this particular story is perhaps most useful for teaching, is about the proper scale of human concern. We have a tendency, as a species, to treat our current moment as the one that matters. The political crisis of this year, the climate anxieties of this decade, the technological transitions of this century.
All of it feels, from inside the moment, like the defining frame for human experience. Toba is a useful corrective. It is a reminder that 74,000 years ago, there was a morning on a tropical island that was, for reasons no living thing could see coming, the most destructive morning of the last 2.5 million years. The people alive that day had their own concerns. They did not know what was happening. They did not know that the sky was about to fill with ash, or that the climate was about to shift, or that their descendants, 74,000 years later, would spend decades arguing about whether their numbers had been crushed or merely reduced. They lived their lives the way you live yours. They attended to their own day. They worried about their own problems. And then something happened to them which they did not understand, and they either survived or they did not. And either way, they vanished into prehistory, and all that remained of them is what we carry. This is not a dark thought. It is a calibrating one. You are, right now, one person in a very long line. The line stretches back through Toba, through every ice age, through the emergence of our species from earlier hominin forms, through the long, slow unfolding of mammal evolution after the dinosaurs, all the way back to the first living cells. You are, in an unbroken chain that has taken 4 billion years to produce, the most recent product. You have, with you in this dark room, the accumulated history of that chain. None of the people in the chain got to know how it would turn out. None of them knew whether their children would live or die. None of them knew whether their kind would survive. They passed their life forward anyway. That is what the chain does. Tonight, if you are about to sleep, the chain is continuing. Your breath is slow. Your heart is still. Your body, which is the accumulated product of every survival along the chain, is quietly metabolizing, quietly regulating, quietly doing the work of continued existence. You do not have to think about it. The work happens on its own. 74,000 years ago, on the morning of the eruption, the ancestors who carried the genetic code that would, eventually, make you, were sleeping too. They were sleeping on the African savanna, or in a cave in the Levant, or along a riverbank in the Arabian Peninsula, or in a shallow rock shelter in southern India. They were sleeping as you are sleeping. They did not know the morning was coming. They did not know that thousands of kilometers away, a volcano was about to empty itself into the sky. They had their own slow breathing to attend to, their own bodies to maintain in the quiet hours before dawn. And they slept through what came next. Their species slept through it. We are, in that sense, what sleeping looks like when it succeeds. But as you drift towards sleep tonight, maybe you can imagine it. The warm darkness of a Pleistocene night, 74,000 years ago, on the African grasslands where the people who would be your ancestors lay among their kin. A fire in the distance, the smell of grass and dry earth. Stars overhead in a sky not yet dimmed by ash, which is coming, which is already in the process of happening at a place none of them could point to, which would, in a few days or weeks, turn their sky a color they would have no name for. They slept anyway. They woke to whatever came. They lived their lives. They had their children. Their children had children. Their children's children had children. And somewhere, tens of thousands of years later, the line passed through the particular ancestors who, in whatever combinations the generations demanded, became you. 2 mornings, 2 sleepers. One of them under an equatorial sky 74,000 years ago, in the last quiet hours before a volcano changed their atmosphere. One of them listening to a story about it tonight, in a warm room somewhere under a 21st century sky that is, for now, clear. 2 sleepers, 2 breaths, the same genetic code folded into both bodies, the same tendency to keep going. The caldera is still there. The lake is still there. The ash is still in the ocean floor and the polar ice. The bottleneck is still written into your cells. And the morning, the actual morning when it all happened, has long since ended. It ended, probably, on a specific day in the late summer of a year we cannot name, 74,000 years ago, when the pyroclastic flows finally stopped pouring out of the wound in Sumatra and the last of the ignimbrite came to rest. After that morning, the world kept turning. The sky eventually cleared. The forests eventually came back. The people scattered across the landscape eventually had children, and their children had children, and the line that would become all of us kept itself alive. Sleep well, descendant of a winter. Good night.